Hi. Previously, we've been discussing Gaussian, Cauchy-Lorentz and void functions. I focused mainly on the width of these functions. And today I would like to focus on a Gaussian beam. So let's start with a Gaussian profile in 2 dimensions, with E0 being the maximum intensity. We have e to the power of minus x squared plus y squared over w naught squared. The maximum of this intensity profile is at the origin. From Fresnel's diffraction, we can write that E at point x prime y prime z equals I E naught over lambda times z e to the minus I k z, and we have integral minus infinity plus infinity. This profile e to the power of minus x squared plus y squared over w naught squared, and times e to the power of minus ik over 2z, and here we have x prime minus x squared plus y minus y prime, y prime minus y squared, and dx dy. So we have 2 planes. Here we have z, here is x prime, y prime, here is x and y, and the next one is y prime, x prime, and here is x without prime, and here is y. Okay, so we have x, y plane and x prime, y prime plane. The propagation direction is z. So in this plane we have some point x, y, and in the next plane we have x prime, y prime. And we are calculating the intensity, the electric field intensity, at the point x prime, y prime. Here is the origin, so this distance is z. So at point x prime, y prime, at z, we have the electric field described by the Fresnel's approximation. And this is our profile. E naught times e to the minus x squared plus y squared over w naught squared. Okay, we can separate these integrals because the solution for x and y is exactly the same. So we can write that the electric field Ex equals just the integral from minus infinity to plus infinity, and we have e to the minus x squared over w naught squared times e to the minus I k over 2z times x prime minus x squared dx. So we have to solve only this integral, and as the solution for x and y is the same, then the solution on e is just ex times ey, and as the solution is the same, it will be just squared. And the solution to this integral is ex equals square root of pi w naught square root of 2z over square root of 2z plus I k w naught squared and we have minus I times 2k zx prime squared over 4 z squared plus k w naught squared, and this is also squared, and once again e to the power of minus kw naught x prime squared over 4z squared plus the same term kw naught squared, and this is also squared. Okay, so this is the solution. The solution for EY is the same, except that there is, instead of x prime, we have y prime, and the solution is the same. So let's write the final solution for EY and for E. So now let's write solution for E, which will be, here we have I E naught over lambda z times e to the minus I k z, and here is the integral, so the solution is pi times omega naught squared to z over 2z plus I k w naught squared, and here we will have, because we have this squared, because this is the solution of E, is this IE naught over lambda z e to the minus ikz, and the solution EX times solution for EY. So we have this term, this is EX, EY, so this is squared, and we have e to the power of minus I 2kz, and there will be x prime squared, so there will be plus y prime squared over 4z squared plus kw naught squared times e to the power of minus, and here will be kw naught, and this will be squared, and once again we will have x prime squared plus y prime squared over 4z squared plus kw naught squared, and this is also squared. Okay. So now let's introduce a new variable. Let's assume that r prime is x prime squared plus squared y prime squared. Okay, so we have a radius in this x prime y prime plane. So let's simplify this. So here is z, here is z. We'll have I e naught times pi omega naught squared over lambda. This will be 2 times, and here will be 2z plus I k w naught squared. And here is e to the power of minus a k z times e to the power of minus 2kz r prime over 4z squared plus kw naught squared times e to the power of minus kw naught r prime squared. Oh, I'm sorry, you can see anything. 4z squared plus k omega naught squared, and this is squared. Okay, so we have a final solution on the electric field in x prime y prime plane at z. We have a few terms here. The first one describes the phase of the plane wave. The second one, this one, describes the curvature of the phase front of this beam. And the last one describes the transverse distribution of the electric field. So, and now we will focus on the last one, on the last exponent. And we know that W naught, if we have even in 1D, a Gaussian profile, and previously we discussed the width for I naught for the intensity, and I told you that W naught appears for I naught over E squared. But if you take the distribution of the electric field, and here we have E naught, then the same width will be for I naught, for E naught, sorry, over E. So it will be at the point where the electric field drops E times, or at the point when the intensity drops e to the power of 2 times. Now we derive the electric field, so W naught is for E naught over E. If you want the electric field to drop E times, then it means its exponent must be minus 1. So this term must be equal to 1. So K W naught R prime squared over 4z squared plus kw naught squared must be equal to 1. Here is minus, so it will be 1 over e in this case. So we have k squared w naught squared r prime squared, and these are equal to 4z squared plus k squared omega naught to the power of 4. R prime actually is the radius, so it will be the width. Actually, R prime is the width. So R prime is the width at z. So we can write that the width for z equals 4z squared over k squared w naught squared plus w naught squared. It is also squared. Okay. So w squared at z equals omega naught squared times 1 plus 4z squared k squared w naught to the power of 4. So let's take the square root of this, and we have width, which equals w naught square root 1 plus let's say 2z over k w naught squared, and this is squared. So now we have an equation describing the width of the beam at the distance z. We can rewrite it slightly. We know that k is 2 pi over lambda, where lambda is the wavelength. So omega z equals omega naught square root 1 plus 2z over 2 pi over lambda. So here is lambda, omega naught squared. So this is w naught square root 1 plus lambda z over pi times omega squared. And here is squared, obviously. Okay. Sometimes this relation is written in the following form: 1 plus z over zr squared, where zr is pi omega naught squared over lambda, and this is called Rayleigh length. Keep in mind that this lambda is a wavelength of a medium in which the beam propagates. So actually this lambda is lambda naught, so the wavelength in vacuum, over the refractive index. So now we can write that this Cr is actually pi omega naught squared times the refractive index over lambda naught. So the Rayleigh length depends on the refractive index. Maybe now let's take a look at the Rayleigh length. What is Rayleigh length? If we substitute z with zr, so we are at the distance z, which is equal to zr. Then we have zr over zr, which is 1. So we have square root of 2. It means that for z, which is equal to zr, the width is w naught square root of 2 times. Rayleigh length is a distance at which the width increases square root of 2 times in comparison to the narrowest point to the waist. So now let's take a look how the Gaussian beam behaves in space, how it propagates. This relation describes the width of the beam. For z, which is equal to 0, we have square root of 1 times w naught. So at the beginning, for z, which is equal to 0, we have a width w naught. Okay, so here is w naught, here is w naught. This is our beam cross section. And as it propagates, as the z increases, the width also increases. And it rapidly increases its width. But when z is much larger than the Rayleigh length, this plus 1 can be neglected. So if we assume that z is much larger than zr, or much larger than 1, we can assume that the width equals just w naught times z over zr, which means we have w naught over zr times z. So the width increases linearly with z. So at some distance, this should be a straight line. Because as the z increases, the width increases linearly. Here is some W. See. Okay, and now, so we can approximate the width far from waist. This point is called waist because here the beam has the narrowest point. And far from waist, far from this narrowest point, we have a linear increase of the width W. Here is also W. See. So we can also calculate some angle of diffraction. Let's say this is a half angle of this diffraction. So we have tangent theta equals WZ over Z, but we can approximate that tangent theta is approximately equal to theta. So we have theta being approximately equal to WZ over Z. And far from waist, we have W0 over ZR times Z. So we have W0 over ZR, and this is times Z over Z. So Z cancels out. So finally we have this angle W0 over ZR, which is the angle of diffraction, half angle of diffraction actually. The full angle will be 2 theta, so the full angle, let's see, the total will be 2 times theta, so it is 2 times W0 over Rayleigh length. So using this relation, the Rayleigh length, we can write that 2 times theta, the full angle of diffraction. This is sometimes called the angular spread, so this is 2 times theta equals 2 times W0, and here we have the Rayleigh length, so this is pi omega naught squared over lambda, so this is times lambda, so it equals 2 lambda over pi omega naught. So this is the angular spread far from waist. So the beam increases its width linearly. So this angular spread equals 2 times lambda over pi W0. So let's take a look at this expression. So this angle, which describes diffraction, increases with wavelengths. So if we have, for instance, a beam of a wavelength 800 nanometers, this angular spread will be lower than for 1000 nanometers. So the longer the wavelengths, the quicker the diffraction. So this diffraction angle, this angular spread will be greater for the greater wavelengths. So if we have ultraviolet beam, then it will not spread so fast than the infrared beam. Moreover, if we have a very narrow beam, so this W0 is very narrow, a few micrometers, this diffraction angle will be much higher. So the narrower the beam, the quicker the diffraction. So the wider the beam, the slower the diffraction. So for instance, if we have a beam of W0 3 micrometers for 1550 nanometers, it will diffract quickly. If the beam is wider, 3 times wider, it has 9 micrometers, the diffraction will be slower. Here is an example for different wavelengths. We have the same W0 of 7 micrometers and a beam of 850 nanometers, which diffracts slowly, at least much slower than the beam with a wavelength of 1550 nanometers. You can compare the output widths of both beams at the distance of 1000 micrometers. For 850 nanometers, it's much narrower than for 1550 nanometers. That's it for now. Thanks for watching, and I hope you've learned something about the Gaussian beam propagation. See you next time. Bye.